Thank you very much for coming to my talk after lunch. Hope you don't sleep. I'll try to keep you entertained. My name is Ignat, and today we're going to talk about Linux namespaces. Who yesterday came to my talk? Oh, damn it. I wanted to recycle some of the jokes, but okay, I'll repeat some of those. So anyway, so I work for Cloudflare. Everyone here knows what Cloudflare does? Who doesn't know Cloudflare? Okay. We do internet, just in the simple terms. A little bit about myself. I do Linux at Cloudflare. I'm a die-hard Linux fan. That's why I'm presenting from a Mac. This is what I mentioned yesterday. I like system security and performance, and I enjoy low-level programming like Linux kernel drivers, bootloaders, and other stuff written in unsafe programming languages. Have a lot of cover in this talk, so this is the agenda. First, we'll talk about containers in Linux and how they're implemented. We'll dive into unprivileged user namespaces. We'll take as an example like how you can sandbox an application on Linux. Like Google Chrome does it. Let's discover some bugs under Linux namespaces and learn basically how to effectively protect from them. All right, let's talk about containers. Who here knows the difference between a virtual machine and a container? Not many people, okay. So, containers on Linux are different from virtual machines, but with virtual machine you kind of have a virtualized computer, but with containers you can have processes or applications running, but the underlying kernel is the same. And the way how containers are implemented in Linux is a container is basically a collection of namespaces. So in the beginning of this talk, I will actually try to break down some of the most popular namespaces. There are many of them, and what you can actually do with them, like each namespace does for you. So let's start with the mount namespaces, but to actually discuss mount namespaces, we have to revise what is a mount tree on a system, right? So mount tree is like a simple data structure. So if you're running Linux or any Unix-based system, so you have your root file system, usually mounted at, like /root, right? Here. And then underneath, you can create different directories and mount different file systems, right? So usually, like, you can have a different boot partition, which will be mounted as /boot. Have a special device file system mounted as /dev. Sometimes home directories contain different file, like dedicated on different partitions and different file systems. TMP file system, like the in-memory file system, and others, right? And special file systems. So yeah, like everyone has this mount tree, right? So now, if we project that to the mount namespace, what happens when you create a mount namespace? And mount namespace are basically the first namespaces introduced into Linux. So the idea behind mount spaces, you create a name. All namespaces are created with either with the clone or unshare system call. So when you and then there you could specify which kind of namespace you want to create. So if you want to create a mount namespaces, what it basically does under the hood, it kind of creates an exact copy of the mount tree into the new namespaces. But the idea, like, why do we need that, right? The idea is that this is like the system name mount tree, and this is like your own private mount tree. So the idea behind that like once you have the copy of your private mount tree, you can like interact with it without affecting the overall systems, right? So look, for example, you can unmount some file systems, and you can even mount new file systems. So you can create a directory and mount something there. Generally, there are restrictions, but yeah. So why is it useful? Like, if you used containers, for example, when you launch a container, right, you can, for example, launch a Red Hat container on a Debian system or vice versa, right? So you can get a different file system inside your container, which actually gives you that feeling of a virtual machine. It's kind of like you have a different environment, but in a nutshell, you don't have a full virtual machine. You're still using the same host machine with the same underlying kernel, but like the file system is different, and this is what gives you the feeling of being inside a virtual machine, right? And the other thing why it's very useful is also for security purposes. So before namespaces were introduced, if you wanted to sandbox an application, you use a thing called chroot, right? Or an alternative technology called jails in Mac OS. But the idea behind that is that you have your root file system mounted here, and then you can create a directory file system, and then you call a special system call called chroot and start a process inside the chroot. And the idea is that the process started inside the chroot directory only sees the mount tree up to that directory. So chroot becomes the root namespace for this directory. And basically the whole point of that, if the process becomes malicious somehow, it shouldn't be able to access files on your host file system, like to steal a password or your SSH key stored in your host file system. The problem with this approach that, like, while the idea is great, the implementation has some limitations, and there are still ways on modern operating system where like a chrooted process can still somehow affect files on the host file systems, right? And exfiltrate data, and this is what security researchers are usually calling a chroot escape or jailbreak, whatever is Mac OS thing. And like in Linux, if you're not careful, like the chrooted process can still affect the host file system via bound mounts, not closed file descriptors, various symlinks, virtual file systems, etc., etc. So what containers do, and they utilize the mount namespaces, they take it one step further. So to chroot a process with a mount namespace, what you do, you create a mount namespace, and now you have this copy, not the original host mount tree, but the copy of mount tree. And what they do is they start similar to chroot. They create like a chroot environment for your new process, but then they also called a special system call, which is called pivot root. And what pivot root basically does, it takes your mount tree and like flips it on a side, right? So the new root directory becomes the root, and your real root becomes the old root, right? So it's kind of like becomes like that. And once you change the root, and old root contains your host file system, right? But because it's a mount namespace and you now can operate on this copy, you can basically unmount it, right? And the idea behind here, if your process become malicious, it has nowhere to escape to, right? It cannot affect the host file system because it's in this namespace it's already unmounted. So like there is no access there. Here is a simple example. So in this case, this is my dev machine. It's a simple Debian. So what I do is I list all the mounts available currently on my host. And by the way, this was all copied from a real terminal. Copy-paste, so consider it as a demo, but it never fails. So yeah, these are all the mounts are present on my host file system. So what I do now, I create a mount namespace, and I can do it from the shell via unshare command, and I say like, hey, create me a new mount namespace. Now my shell is executing in the mount namespace, and what I'm doing here, I'm unmounting this thing in my namespace, right? Yeah, and I can check that it actually succeeds. So like run user 1000 is not a mount point anymore, right? But then when I exit the process terminates. So again, I'm exiting both the process and therefore the newly created mount namespace. I'm in a host namespace now, and here I can check that run user 1000 is still a mount point. So like I unmounted that mount this file system in my copy on my of my namespace, but I had no effect on the host file system. Clear so far? Okay, let's talk about network namespaces. But to talk about network namespaces, like let's see what kind of network resources we have in an operating system. Of course, you have with networking, you have the network cards, right? One or several. Then you have your machine has some kind of routing configuration or routing, if you're British. Then you have your firewall configuration, right? And various operating system tunables, configs, or tweaks with respect to networking. So now, with all these resources, we want to create a network namespace. So we call our favorite clone and unshare. And what do we get? What do you think? Copy? We get nothing. We get an empty namespace. It's not really empty. You will have a local copy of a local host interface inside. But the thing is, what you can now do is you can move some of the networking resources to your network space. Not some, like only the network card. So for example, you can move the NIC from the initial namespace, all the namespaces which are available on your host called initial namespaces. So from the initial networking namespace to your private networking namespace. And here you can have separate independent routing configuration. You can have independent firewall configuration, and you can have independent operating system configuration. So like a total copy of the whole networking stack just dedicated to yourself, and you can do whatever you want with it, almost. And the other thing is, which is really popular with networking spaces on Linux, you can create a virtual network card called VS. So basically, these are virtual NICs that always created in pairs, and they act like real NICs, and they are kind of always connected with this virtual cable, right? So like if you send a packet on one end, it will always come out on the other end. But why it's useful, so like you can create this vSpare and move one of the ends of the vSpare to the network namespace. And now you have two network namespaces, two networking stacks on the same system, able to communicate with each other, which is very useful for various cases. So let's see an example. So here I list all my network devices on my host virtual machine, and you see I can have some kind of like several adapters here, one real one and one created by Docker. Now I'm creating a new network namespaces, and again I'm listing all the NICs now, and I only see my local copy of the local host NICs. There is nothing more. And actually, to make networking namespace useful, you have to always enable the local host interface first before you can do anything. Yeah, and now it works. So why is it useful? It's very convenient to use, for example, in testing, in kernel development, or other networking applications, because you can actually test like a client and a server on the same machine without resorting to a virtual machine. So, for example, this is my host namespace, and this is my newly created network namespace. So what I do here, as I mentioned previously, I'm creating a vSpare, and I'm saying that the adapters will be called left and right, right? And I'll tell also immediately in the command that I should move the left part of the vSpare back to the namespace number 1, the initial namespace. So namespace number 1, so like one of the ends will be moved to this namespace. So now we can check, we can list all the adapters, and I can see I have one networking adapter called right? And on my host namespace, my initial namespace, I can also list the networking adapter. And now I have a new networking adapter called left, right? And now I can configure like IP addresses and enable NICs on both ends. So like IP address here, they should be from the same subnet. And now I can communicate between the two namespaces. So like this is how I can do testing. So I can move a server to a namespace and have a client and test the whole networking protocol around it, right? Without affecting each other. And the nice thing about it, like all the resources that created in the namespace have the lifetime of that namespace. So now I exit my process, which is in the namespace, right? And my process gets destroyed, my namespace gets destroyed, and all the resources associated with the namespace get automatically destroyed. So even the viz adapter, which one end was sent to this namespace, also gets destroyed. So like the automatic cleanup is very, very useful for tests. Like the tear down is simple. You shut down the namespace and it's gone. Clear so far? Okay, let's talk about process namespaces. And to talk about process namespaces, let's talk about PID namespaces, sorry. And we need to talk about the process tree. So again, if you start your system, every process on your system has a process ID, PID, right? And the first process ID, which is started by the kernel, has a PID1. So this is your init process. On modern Linux distribution, it's usually the systemd. And systemd starts other processes. So you have PID1, it starts other processes, and these processes can start other processes, and all of them can have IDs. So now that we want to create a PID namespace, so we do our favorite clone and then share call, and we get what? What do you think? Huh? We get 1? Well, technically we almost get nothing, almost, yeah, but 1. So we actually need to create another process in the host namespace which have some kind of ID, non-1 ID, but it will automatically become a PID1 in our namespace. So it will become the root of the PID, right? And then being the PID1 in the namespace, again, it can create other processes, and like, yeah, you can have the same even PIDs repeating over and over again. But the processes, in this case, exist both in the host namespace under some PID and in the PID namespace under some other PID, right? So here is an example. So this is my shell. I can check its PID, and currently it's 7551, right? Now I'm creating a PID namespace, and basically because of the semantics I just showed, I also need to pass the fork parameter. But now I can check my ID. I'm becoming the init namespace, init process in my PID namespace. So I'm PID number 1. Surprisingly, if I go to the proc file system and try to get the PID, I will still get a PID from my host namespace. And this is because this is actually an example of a container escape, because when containers create, it's not enough just to create a PID namespace. You also need to create a mount namespace to mask that if you don't want processes discovering their PIDs on the host namespaces, right? So here I didn't do that, so I can see the PID on my host namespace, and also I can see a mapping like NSPID, so like I can see that in this namespace, the process on the host namespace is mapped to PID1. Also, PS3 kind of like gives you this helpful example. So this is my initial shell, right? And this is what processes are created. I created sudo twice because I used fork, and then I share, and then when you see the bash started S7574, but it tells you also that here we transitioned to a new PID namespace, and it became a PID number 1, and then in the PID namespace we have the PS3 running under this PID. Okay, clear? Let's talk about users. We know users on the system, like you have the root, which has a user ID 0 usually. Actually, root doesn't have to be named root, so any user with a user ID 0 is root. Then you may have some, depending on your distribution, some system users called daemon, like SSHD, Nginx. They may have some user IDs. Then you have like actual real users who log into the system, like Ignat, Alice, and Bob. So when you create a user namespace with our favorite system call, so what happens? What do you get? No. Well, technically, you get the same thing, but it's not a copy. It's kind of the same representation, but the thing is what you can do here, you can create mappings in the user namespace. So for example, in my user namespaces, I can remap my host user Ignat to the same user in my user namespace. I can become Ignat in the same user namespace, like 1000 to 1000, which is not very interesting or useful. What I can do also, I can remap Alice to become the privileged daemon process, which is more fun. And the most fun, I can remap Bob, a regular user on my host file system, to become root in my user namespace. Cool, right? So let's see an example. Here is my ID. I'm Ignat. My UID is 1000, right? I create a user namespace and share, and now by default, and share maps you to the user ID 65534, which is nobody, and the system tells me that. So I exit my user namespace, I create another ID, and I can actually supply mappings that I want myself. So I'm telling the system to map my user to 1 and my group to 1, and then I can run the ID, and now I'm suddenly daemon on the system. And this is like the example. I can actually even map to non-existing UIDs. So like I can map myself to user 1337, and my system even doesn't have such a user. And the shell tells me I have no name. Yeah, but I still have the user ID. But I have no name, as in a hacker movie. The most interesting case, I can tell the system to map myself to root. And here I immediately become root. Right, and the ID I'm 0 and everything. So let's talk about unprivileged user namespaces. So if you are attentive enough watching this demo, you will probably notice the difference. All the namespaces that I presented, I created with sudo, like the mount and share namespace. I need to run sudo and share, right? Versus when I created a user namespace, I didn't use sudo. Right? So here I need real root privileges to create other namespace, but I don't need any privileges to create a user namespace. And moreover, I don't even need privileges to create a user namespace, but also I can map myself without any privilege to become the user, to become root in the namespace, right? So it's interesting. So like I don't have any privileges, I create a namespace, and suddenly I'm becoming root on the system. Yeah, so it's it unlimited power and the ultimate privilege escalation you can always use.
What happens to the files you create?
Good question. It depends if you have a mount namespace. Yeah, if I didn't have it, if I create the file system from the host perspective, it will be as if my user created the files. I don't remember. It depends again on your permission. But we'll get there, okay? So, yeah, I mean, it's not an ultimate privilege escalation, obviously, because all the hackers will be using that and will be in a bad position. So why do you need unprivileged user namespaces in the first place? So the thing is, in the system, user namespaces are kind of like the permission manager for other namespaces. So for example, I'm an unprivileged user on the system, and I can create a user namespace and map myself to root. But there, for example, I can check that the /tmp is not a mount point. So now, because I'm root, why can't I use a mount operation, right? And I want to mount a new file system on /tmp, but I still get permission denied, even though I seem to be root. So why is that? Because on the system, so you have all these initial namespaces. So you have initial user namespace, initial network namespaces, mount and PID namespaces. So what we did here, on Linux, the user namespace is set to be owning every other namespace in this set, right? So what we did here, so we created a new user namespace, right? But when we tried to issue a mount command, so we didn't create a mount namespace, so we tried to interact with the initial mount namespace because we didn't create a new mount namespace. And the permission models in Linux is doing checks against not your current user, but the user that created a particular namespace. So in this case, when I'm trying to interact with the initial mount namespace, the permission checks are done against the initial user namespace. And the initial user namespace, I'm not a privileged user, so therefore systems does not me allow to do a privileged operation. Yeah. So what can I do once I'm a new user, a privileged user in my user namespace? I can create other namespaces. So I can actually create a new mount namespace, which will be a copy of the initial mount namespace. But now I can interact with that because the permission checks will be done, you know, like according to my user ID in my namespace, and it should be allowed. So let's see an example. So again, it wasn't allowed, but if I create a new mount namespace, now I can easily mount a temp file system on the /tmp, and it just works. Right, and we can check that it's a mount point. Okay, so this combination gives you a nice building block to do unprivileged containers for code sandboxing. So why you want to do that? So from a high-level perspective, you have your infrastructure, you have some applications running, right? Which is, for example, a web server. And then you have like internet people, you have good people and bad people. They're sending both good and bad traffic, and like bad people always try to exploit your application, right? So, and if you don't have any sandboxing in place, not only your application get exploited, like your whole infrastructure might get exploited. So what you want to do is like you want to sandbox your application to ensure that any bugs you didn't discover cannot be like used to exploit your whole system, potentially on your application. And like, what is the best example of a network-facing application that receives untrusted input? It's probably a browser, right? You download a lot of HTML. So Chrome multi-process sandbox model is like very complicated. So what they do, they have several layers of sandboxing. So what they try to do, first, every tab you run in Chrome is run actually as a separate process on Linux. So you already have the address space isolation between the processes. So if one tab gets compromised, it cannot affect other tabs. So yeah, address space isolation. Secondly, they actually use these unprivileged user namespaces and various other namespaces to create these virtual containers around each process. Yeah, and on top of that, they also use a technology called seccomp, which was introduced here last year and some other years as well. So it's like to further really limit what this thing can do. So like if there is a bug in the HTML parser in Chrome, it kind of has to go up several layers of sandboxing to actually affect the system. Yeah, and if you're interested in more detail, this is a reference where you can look for it. Yes? I mean, it is for Linux, but they have similar they try to use similar technologies on other operating systems available. I'm not, for example, a Windows expert. I'm not sure if all of it is true on Windows, but I do know most likely they still run tabs as separate processes, so that's definitely true. Yeah, there are some other users of unprivileged user namespaces, so a project called rootless containers, which allow you to run your Docker without root, which is very useful. Systemd core dump also uses unprivileged containers to actually, like when your system creates a core dump, they want to process it, but they don't want to accidentally like process malicious input, so they fork themselves into the container and basically process a core dump in the container. And again, various testing frameworks, fake root applications, all of that other thing that requires you to potentially run stuff as root, but you don't want to give extra privileges to it to run as root on your real host system. So in a nutshell, we can say that unprivileged user namespaces is a great tool for applications to create effective sandboxes and harden their security, right? Well, maybe not, right? So if you're, who here uses Arch, like you say? By the way, use Arch. Oh, cool. If you read, this is from Arch Linux hardening guide, but you can like read any Linux kernel security hardening guide, and you may see that most of these guides, for some reason, recommending disabling unprivileged user namespaces. So yeah, if you talk to security folk, the first thing they will say, like, disable unprivileged user namespace, disable unprivileged user namespaces, because it's bad for security, which is weird, right? So like, we just discovered that it's a good sandboxing technology, but everyone wants to disable it. And to give you an example why, let's talk about a kernel bug in Cloudflare, which is like from 2022, but it's even older than that. So a long, long time ago, one of our engineers actually discovered the kernel bug in our Jira. They were experimenting with some networking configuration, and they realized they can crash the Linux system with some specific configuration. And you can see the bug is quite old. It's from 2019 years. Like, we are responsible for the Linux kernel, so we actually reported that bug upstream, but technically we didn't get any attention. So like, nobody even responded, and we didn't know exactly how the TC subsystem works inside the kernel, and we didn't get any output. Nobody responded to that bug, and that's natural, because this is a reproducer to reproduce the bug. But the problem is, like, you need like super user privileges, right, to do that. So basically, is it critical? Well, no. Like, so the system administrator can crash a system. So like, yeah, it's not like, yeah, it is a bug, it needs to be fixed, but it's not that critical, right? Because you can do it officially in Linux by running this command for testing, right? But fast forward to 2022, and we come back to, like, remember the networking namespaces, how they work. Like, hey, well, we're thinking, like, after all, why not? Why not try to reproduce the bug in the kernel network, in the Linux networking namespaces? So, and here is an example. I'm actually running, the bug was fixed already in the kernel, but I'm running on a buggy system now, and I'm an unprivileged user. This is the last version which had the bug. So yeah, I'm showing that I'm fully unprivileged. I'm just user ID 1000. What I'm doing here, I'm creating both the user namespace and the networking namespace. I'm again configuring my local host interface up, and then I'm trying to run the reproducer from the to reproduce the bug. And after you configured your system, all you need is one ping. You need to send one packet through the networking device, and if you basically run this, like, your system will crash. So now it becomes more interesting, right? Because I could, for example, I could run my unprivileged container in our Kubernetes cluster with no privileges, and I can go and crash a Kubernetes host, and I assume you could crash like a cloud provider providing you a Kubernetes service. And turns out we're not alone here. So this is not the only bug which become a security vulnerability just because unprivileged user namespaces exist. And like a simple scan of the CVE database, there are many more of them, and they keep popping up. So why do these bugs become CVEs? Why does this happen? Is this because the user namespaces are bad? Well, no, they're actually doing what they're supposed to do. The problem is elsewhere inside the kernel. So this is like a pseudocode of some kernel functionality, which was originally only available to privileged users. So you basically get some privilege checks, okay, if capable sysadmin, and then do some privileged stuff. And the problem with that like over time, the Linux kernel code batch is huge, that this thing may contain bugs, right? But previously it wasn't a problem because only like privileged user can get to this point in code execution. But the availability of unprivileged user namespaces allows any user on the system to actually get to that code. And if that code is buggy, you can trigger bugs in the Linux kernel as an unprivileged user, which is bad. That's why all the security folks tell you that user namespaces are bad. So what can we do about it, right? So well, we can follow the advice, and we can disable user namespaces in our kernel configuration file, which is, or you can use a special ccTL. So there is a how many user namespaces you can create, and usually it's a big positive number. So you can create a user namespace, but if you set it to 0, so you cannot create user namespaces anymore. So you can disable them even without recompiling the kernel. However, the problem with that approach, it's kind of like cracking a nut with a sledgehammer, right? So you kind of like disable the whole useful thing, which allows you to sandbox your applications, as well as like having a good testing frameworks for the other code. Debian operating systems, and then it was, and therefore Ubuntu also adopted, and then it was ported to Arch Linux, also introduced another sysctl that instead of completely disabling user namespace, you can only disable unprivileged user namespace. So, but that patch was never accepted upstream. So like basically when you have the sysctl enabled, and you can find some guides on the internet doing so. So if you are a non-root user, you cannot create a user namespace, but if you're a root user, you can still create user namespaces. So Docker works on your system. But again, this patch was proposed by Debian, but it was never accepted in upstream kernel, so it's not available on all distributions. So I know it's available Debian, Ubuntu, Arch Linux, but not on Red Hat, for example. Yeah, and the idea why it wasn't accepted, because the whole kernel community is kind of divided into camps, right? From one side, we say like, well, should we have unprivileged user namespaces? And the security people say like, we need to disable unprivileged user namespaces because they create more vulnerabilities. Actually, they don't create more vulnerabilities, but they open the attack surface to unprivileged users more in the kernel. And the other side of the camp says like, no, we need to keep unprivileged user namespaces because they allow us for more secure designs. And the whole problem with unprivileged user namespaces is not because they exist, but because other bugs in the kernel exist. So let's just instead fix all the bugs, right? So let's just fix all the bugs in the Linux kernel. Probably not will work very well. So should we disable or keep? Well, actually, let's do both, right? So the idea here is, how do we allow some applications that we trust to create user namespaces, our testing framework, our services that require sandboxing, while prohibiting the others, like a random app that you download on the internet cannot exploit a kernel bug on the system. And for this, you need some kind of policy now, right? And policy in Linux is equal to some Linux security module implementation. Who here worked with Linux security modules? Maybe you know SE Linux. Who here works with SE Linux? So SE Linux is like one of the main example of Linux security modules you can use to do it. But the problem with the SE Linux, if you ever worked with the SE Linux, defining a good security policy is very complicated. So first of all, it uses a custom language to describe your security policies. Also, if you want it to be really, really fine-grained, so you have to do a lot of stuff. And basically, you have to have a dedicated team just to managing SE Linux policy for a complicated production setup. So we actually opted not to doing that. What instead we started investigating is to use the BPF LSM. Who've been to the eBPF talk, Introduction to eBPF? Yeah, so you kind of have the idea of like what eBPF does, but like usually eBPF is used for tracing or performance investigations, but here you can actually write your security policies in eBPF programming languages. So for example, you have your kernel, it implements some system call. What you can do is you can write some policy as a BPF program, attach it to a particular hook in the kernel, and then when some process runs, and some process, for example, in this case calls the clone system call, we can check if it's allowed to do so and either allow unprivileged user namespaces or deny for each process. So it will be very, very fine-grained. The problem with this approach, we try to select a proper security hook inside the Linux kernel. which kind of created a little bit of bad experience for our operations people, because the way how it was implemented, if you attach a policy which prohibits you creating an unprivileged user namespace, the actual user of the application will not get a permission denied, will get a cannot allocate memory error code. And this is because the hook we selected is implemented like this. So the error is defined in mem. This is where we attach stuff. And this is where prohibit creating the user namespace. But as you can see, we kind of ignore the error code and just return here mem. So which create a lot of confusion for our SREs actually. Like, why is it reporting no memory? Because we have a lot of memory on our servers. So to address this, we wanted to propose a new security hook just for this purpose in the Linux kernel, which will be accepted upstream. But there were dragons with this approach, and you can read the details here. The problem with that the maintainer of unprivileged user namespaces is from this camp. So they strongly believe that we should not ever disable unprivileged user namespaces, and we should not police them in any way. And yeah, they kept refusing our proposal, and we actually spent 6 months arguing that the security community needs it. Luckily, like, Linux kernel is the biggest open source project on the world, so it's kind of democratic. So it's not like a decision of a single person, right? No, wrong. This is a guy who decides. And luckily, Linus actually took our position and said, like, okay, if we have security policies policing, like opening a file, why shouldn't we have a security hook policing like a complicated thing like unprivileged user namespaces? So this is what his response. It's very funny. You can read it. Linus usually, when he's angry, writes funny text. So overall, we got our code merged, and from Linux 6.1, you have a new shiny security hook where you can attach a BPF policy to actually really fine-grained police and privileged user namespaces. And here is a full feature example. You can later copy-paste from the slide. Here it's like, it's not a root security policy. It's kind of, it just shows that it works. So this is our new security hook that we introduced called user ns create. And in this particular example, I'm creating a toy policy just to show it works. So I'm saying in here, if my process name starts with a T, I allow it to create unprivileged user namespaces, but if not, it returns permission denied. And basically, if you went to the BPF talk, I hope they showed you how to compile BPF applications, but if not, you can run these commands, so you can compile your policy into a program. Then, because the BPF ecosystem is very weird and developer unfriendly, you need to generate a skeleton from this program, and then it will produce you another program which loads that policy into the kernel. So this is the problem that loads it in the kernel, and from this point, our policy is kind of enforced. So going back to that, we again need to compile this real program, and when we load it, our policy is now enforced in the kernel. But that's not interesting. The interesting part is how it works. So again, once the policy is loaded, it's enforced. So now I try to create and unshare an unprivileged user namespace using unshare, and I'm getting the proper error code that operation is not permitted. But remember how our policy was implemented. So if I rename the unshare binary to /trusted, I can suddenly create a user namespace because I'm kind of allowed by the policy. So, so basically, the similar approach, but much more complicated, we now are using in production. So we know we have an allow list of services or applications that actually need unprivileged user namespaces for sandboxing, testing, and other stuff. But for any other software which is not in the allow list, we don't allow unprivileged user namespaces. I think that's it. So conclusions: unprivileged user namespaces are a nice building block in Linux, which you definitely explore for better application sandboxing, rootless containers, and reduced need for setuid programs. However, uncontrolled user namespaces may have widened the system attack surface by escalating simple kernel bugs to actual security vulnerabilities, and we can still get best of both worlds by utilizing Linux security models to provide really fine-grained access for application to unprivileged user namespaces. And I highly encourage you to consider, if you want to employ any Linux security module, to employ BPF LSM, because it's more a new developer-friendly LSM. So now you don't have to write these complicated SE Linux policies. You write your policies in a simple C programming language, which is understood by most developers, so they can actually collaborate on these policies with you. So like if now in production, if someone needs to add a service to an allow list, they don't create a ticket for us, they just send a pull request to the policy, and it all works. Thank you very much. Here are some links, links to the man pages describing the various namespace functionalities. Everything that I presented today is covered by 2 Cloudflare blog posts with all these examples and much more. I highly encourage you to go and read them. Thank you very much, and I'm happy to answer questions. Going back to your question about the file, I kept thinking about it, but I don't remember actually. Like it depends on like how many namespaces you configure. I know at least in Docker, if you run a Docker, right, and you create a file as root inside the Docker, it will also be root outside the Docker. So this is like one of the problems. But I guess you can reconfigure it with a user map. I think there is another namespace which actually can support remapping the files back from root to your proper host user if you need to. Any more questions? Going once, going twice. Thank you.